Thank you. So before officially starting, I'd like to thank all the organizers for their great work putting together this wonderful workshop. I certainly have chosen this one over the other conference. So I'm going to talk about phases and how to detect them. So, and I guess one very important aspect of our understanding of the universe and of the physical world around us is that they are matter and matter has phases. And we have been um, studying phases since, well, we first entered elementary school, and then we were told that water actually have phases. So if we take water at room temperature, um, these are in liquid form. If we lower the temperature, then at roughly 0 Celsius, um, uh, then it become a solid. And then we say that there's something discontinuous at this particular temperature, and that mark a phase transition separating the two phases. So, and then we have learned a lot about various other kind of phases in all kind of systems, um, ordinary phases, topological ones, and a bunch of others. And then, but in general, the problem of detecting and separating phases are not so simple. So, which is even already present even in this very simple case. Namely, if we heat water to 100 Celsius, and we know from daily experience that the liquid form of water will turn into the gas form, namely water vapors. And then there is a phase transition happening here, very similar to what's happening here. But then this is not a phase transition that separates two different forms of phases. It's a phase transition, but it's actually the same phase on both sides. And one way to see this is by turning on the other parameter, namely pressure. And then we'll have the phase diagram, which roughly looks like this. And then here you have the water phase, but there's actually a path in this bigger phase diagram that smoothly connect these two phases. So it's certainly not true that whenever you observe some discontinuity in one family of theories, then you can say that there is actually a phase transition. You cannot say that this phase transition will actually separate two phases. So what's actually a good way of detecting phases? One way of doing that is by coming up with certain order parameters. And we are by now somewhat familiar with this, namely in, let's say, Ising model. Then there you have two, again, phases separated by the system at certain critical temperature. And then one can come up with an order parameter to distinguish the low temperature ordered phase with the high temperature disordered phase. But in real life, it's very hard to come up with enough order parameters because, well, even for water, there are many phases, and in reality, they are not really distinguished by coming up with order parameters. Instead, you try to explore the entire phase diagram and then really finding those phase boundaries. So I guess it's a workshop on BPS dynamics and quantum mathematics, and I would get killed if I keep talking about water for 1 hour. But in the world of supersymmetric theory, actually the situation is much better, because for supersymmetric quantum field theories, there are some natural order parameters. So because they are quantities that are protected by supersymmetry, they are often referred to as BPS quantities. And there are many examples, starting from the simplest ones, namely indices, and more interesting and delicate ones, namely certain algebra. Let's say algebra of defects, supersymmetric defects, and all the way up to certain categories or higher categories of defects of higher dimensions. So and these, in principle, can be used as order parameters that help us distinguishing phases of supersymmetric quantum field theories. So let's start with the most basic example, namely the example of a particular index known as the Witten index. So this is, in a sense, really quantum mathematics 101. So this is Witten index in 1D supersymmetric quantum mechanics. So, and this can be defined even with a single supercharge. And for this theory, there is a supercharge, and it has a property that Q squared equals the Hamiltonian. And then, if you look at the representation theory of this algebra, then you already get something interesting. So there are two types of representations. So one type of representation has eigenvalue of h being positive. Well, so some state with E being positive. Then if you act Q on this state, that cannot be zero. And it has to be some other state with exactly the same eigenvalue. So therefore, such state has to come in pairs. And I would denote it, one by B, because that's a bosonic state. So that will equal to square root of E times another state, and that has to be fermionic. And then similarly, you have the following. So Q acting on the fermionic state will equal to square root of E times the bosonic state. So that's one particular representation of this but then you have something special happening when E actually equals 0. When E actually equals to 0, what can actually happen is that Q acting on either the bosonic state can be 0. So it is itself a well-defined one-dimensional representation of this algebra. Similarly, you can have Q acting on some other fermionic state that again equals to 0. That's another representation of this algebra. So bosonic and fermionic states will not have to come in pairs. Then, if one define the index as the number of bosonic states versus number of fermionic states, then it will turn out that this is actually a protected quantity. And this can be computed by just looking at the ground states. So And it's protected in the sense that now, if you have a number of bosonic and fermionic states, so for the states with non-zero energy, they have to come in pairs. And then if you continuously deform it, as long as the process is really continuous, then what will happen is that states have to either leave or enter the ground state in pairs. So here, you cannot just leave a fermionic state, but instead you have to leave a pair. So now let's assume that you have a pair of bosonic and fermionic state has left the ground state. Then, if you again compute this quantity, that would be exactly the same. And either you compute it using the entire spectrum, or you compute it just using the ground states. This number will not change. So it's BPS invariant. So how to use this to actually detect phases? Well, here, this picture actually tells you that sometimes it failed to detect phases because, well, if we imagine varying this Hamiltonian in continuous fashion, and then here, actually these two, in a sense, belong to two different phases. The ground state, there are two bosonic states and one fermionic state. Here, there's only a bosonic state. And then you will say that actually, these should be two different phases. And then this index will not detect it. So in this case, it's it fail or can't detect. But this index is useful in detecting another kind of phase transition, where something more drastic happens. So let me maybe draw another. There's some other discontinuity crossing which I now have a continuous spectrum. And then I can have another system with different weight index. So for example, I can now have maybe 3 and a single. So there are this kind of phase boundaries, and the index on the two sides will actually be different. And then the weight index will be useful in detecting this kind of phase transition. But here, you still have a bit a shortcoming. You can detect the phase transition, but it's not really telling what is going on here. Because, well, for this continuous spectrum, actually you have trouble defining this invariant. Here we have assumed that the spectrum is discrete. So in this 1D example, I have demonstrated that for this invariant, it can be useful. Sometimes it's not very useful, but one can use it for to understand a bit of the dynamics of the theory. So today, the focus is not really one-dimensional quantum mechanics, which is maybe slightly too simple. Today, the focus will actually be three-dimensional supersymmetric quantum field theories. So there, the structure of those theories are going to be more interesting, and they often have many real parameters. So today we'll only assume 3D n equals 1, but for many of you, maybe you are more familiar with the 3D n equals 2 story, and then you know that there are often real parameters like real masses, Fi parameters, and other kind of parameters, so on and so forth. And then you can again ask what happens if I vary those parameters. And sometimes you have a similar phenomenon. So apparently you encounter some phase boundary where you have a lot of massless degree of freedoms. And then you have two like candidate for phases on the two sides. And then again you ask whether they are the same phase. So for this kind of question, again, you can use an index, which can also be defined for 3D theories. But then you will be more suspicious of whether that's a good invariant or not. So let me give you an example. So that's indeed 3D n equals to 2 example. So one consider this following one parameter family of theories. So the gauge group is U1. You start with some non-trivial transimus level, k over 2, plus k charge 1 chiral multiplets. And then this is a one parameter family because we are varying the Fi parameter. And then when this parameter is zeta is smaller than 0, what happens is that if you look at the determinant equation, it will tell you that all of these are massive and can be integrated out. And at low energy, one should have U1 at level k transimus theory. And then when this parameter actually equal to 0, you have massless degree of freedom. So the IR theory is actually SCFT. But then if this parameter is positive, then you can argue that the low energy description is given by a sigma model to CP k minus 1. So I don't know what's the origin of this particular example, but I first learned it from this paper by Kupsing and Willett, where they talk about a slightly more complicated family. But I can assure you that many one parameter family of theories in the world of 3D theories. So then, now on the two sides, there are two gapped phases. And then you can ask, are they the same or not? Whether the low energy effective theory of this is actually, again, described by U1 transimus theory. And one way to try to find the answer to this problem is, again, to compute the index. So what happens if we actually do that? So if one compute actually the index, it would be actually k on both sides. And that's not something too surprising. So here, what is this index counting? Well, that's a T3 partition function, and it actually counts the BPS line operators in this theory. And in U1 transimus theory at level k, indeed you have k different lines. So you get k. Here, from this point of view, the Hilbert space is given by quantum K theory, the k minus 1. But quantum K theory, it has the same dimension as ordinary cohomology. And the ordinary cohomology of CPK minus 1, that's again k-dimensional. So actually not only you have index equal to k on both sides, you actually have the BPS algebra to be identical. So on one side, that's BPS algebra for the line operator given by U1 level k. So that's basically given by the following. And then you exactly have the same thing on the other side, because this is also isomorphic to the quantum K theory of CPK minus 1. So at the level index, you will not be able to distinguish them. At level of BPS algebra, still you will not be able to distinguish them. But are they the same phase or not? So, hmm? Imagine there's a big space of theory. If I can continuously go from one to the other, then continuously without any kind of discontinuity. So if I'm only interested in gap phases, I will not be able to allow. Yeah. Yeah, yeah. That depends on whether this kind of thing, discontinuity happen in the middle, whether I have a continuous spectrum or not. Right, so that could be one criterion. So if I'm, well, but the problem is that you can imagine there is a bigger theory where I can actually do the crossover, like that, connecting water and, yeah. Yeah. So because the space of theory is infinite dimensional, you are never so sure whether there cannot be a path. Instead, we try to ask the opposite question, whether I can come up with a quantity that is actually continuous and the good deformations. And then if they actually take different values, then we know that they are different phases. So any other? Yeah. So you can take UN at level k, then you will be Grassmannian on this side. And then you can take even more interesting thing. But then it will be some reduction of certain, well, it will be still some quantum K theory or some Kähler manifolds, but reduced in some way. Yeah, so the point is that you have to have a Fi parameter here to play this game, and that's only present if this has a continuous center. So if you want to work with some semi-simple group, you better cross it with U1 and then play this game. So. Oh, so here I'm imposing supersymmetry. So here you will be a family of. So I would only allow deformation that preserves supersymmetry. So they are only the same phase if I can find a path in the space of supersymmetric quantum field theories that smoothly connect them without the gap closing. Yeah, yeah. Yes. Yes. So it's a topological theory, so it's a SQFT in the boring sense. So. So this is a 3D sigma model. If it's a 2D sigma model, it will be quantum cohomology. So this is quantum K theory. Yeah, yeah, exactly. Hmm? Yeah. Yeah. Um, in a sense, yes. So supersymmetry here play the role of the usual global symmetry that protect massive phases. So yeah, I guess that's right. Yeah. Yeah, yeah. Yeah, so the SUK would actually indeed on the Hilbert space. So yes. Well, so you act trivially on both sides, right? So so you act trivially on cohomology. So here at low energy, we will not really see this. So maybe as there's a massive tower that where you can see this, but then if you include some massive tower, you better include other degree of freedoms, which might also break this symmetry. Yeah, yeah. It's supposed to be on R3. Yes, and that's actually a very important point because, well, why they are the same, as Cyril just mentioned. These are actually examples of 3D phases that become the same 2D phases after reduction. So here, um, um, there's a good explanation of why they're the same. So if I actually put a circle in the game, then what happens is that I complexify the Fi parameter. And then this becomes a more familiar story that Witten studied in the 90s, where he relates Valenda algebra with quantum cohomology of Grassmannians, for which this is like a special example. Then there you have U1 WW, gauge WW, U1K, gauge WW model on one side. And then sigma model to, again, CP K minus 1 on the other side. But now the point is that the singular point is actually in complex codimension 1 because the Fi parameter complexifies. And then, indeed, you can find a smooth crossover from one phase to the other. So in 2D, they are actually exactly the same phase. And then from this point of view, these are not very good quantities because they are not intrinsically 3D quantities. They can be defined for 3D theory and also 2D theory. And because of this, they are guaranteed to be the same for the two, even if they can be two different phases in 3D. So then the question is that whether one can come up with some genuinely 3D invariants. So new and genuinely 3D invariant. So I put this in quote because this at first sounds a bit very naive and very stupid. So the invariant that I'm going to take is going to be the space of supersymmetric boundary conditions. So we're talking about supersymmetric theory in 3D. And then you can have boundary conditions, which are two-dimensional. So these are going to be two-dimensional. And then it can be still supersymmetric. And here, there's a choice of what is a supersymmetry. The choice is that it's a 0, 1, at 0, 1 supersymmetry. So namely, the algebra, the supersymmetry algebra looks pretty much like the 1D case. So there's only a single supercharge. But the square of that is just not just Hamiltonian, but instead a combination of the Hamiltonian and the momentum. And why this sounds a bit stupid, because, well, the space of boundary condition, that's very large, and that's some infinite dimensional and very complicated space, and how to actually work with this space. So first of all, there is some structure to this space because of the following. So let's imagine that we have some three-dimensional supersymmetric theory T, and then it has some boundary. So the space of boundary, we will denote it by BT. And then it has, this is naturally module for the space of boundary condition associated with the trivial theory. So why that's obvious? Well, what's a boundary condition for a trivial theory? These are just independent 2D 0, 1 supersymmetric field theories. And then one can stack those theories on top of this boundary condition. So, so if this is some particular boundary condition inside the space of boundary conditions, then I take another boundary condition of trivial theory, which is a 2D theory on its own. Then I can certainly stack this on top of it. So then this define action of this B prime on this space. And in particular, this space itself has action on itself. So it's actually an algebra. But then this still sounds somewhat abstract and hard to work with. Interestingly, there is conjecture. And if we believe that's true, that will tell us everything, that can in principle tell us everything that we want to know about this space. So this is a conjecture by start with the work of Siegel and then Stolz and Techner. Which basically says that this space B trivial has very rich structure. It's a spectrum for TMF. So what is the meaning of this sentence? So here, spectrum is not in the sense of spectrum of quantum mechanics, but in the sense of algebraic topology and Brown representability theorem. So there is a connection between spaces and generalized cohomology theories. So one famous example is the connection between ordinary cohomology or homology with Ellenberg-MacLane spaces. So then their conjecture is basically that this space is conceptually very much like the Ellenberg-MacLane spaces. There's a sequence of them, and then they are compatible with certain interesting relations. So, but today probably I will not tell you too much about this from the point of view of spaces. Instead, I will just tell you some quick things about its homotopy groups. And I guess that's maybe the quickest way to let you have a feeling of what this thing actually look like. So TMF stand for topological modular form. Because they are really, in a sense, a refinement of usual modular forms. So there is actually a map to the ring of, so here, let me denote this by pi star TMF. Then it has a map to the usual ring of modular forms. So what is this? It has a, yeah. Yeah. So BT, I take a three-dimensional theory T. So T is a three-dimensional theory. BT is a space of supersymmetric boundary conditions. And then I can take T to be a trivial theory. And then what's a boundary condition of trivial theory? That's just a 2D theory by itself. And then BT is naturally a module of B trivial. Yeah, because one can stack a quantum field theory on top of this boundary condition. And that's another boundary condition. Yeah, in a sense, it's this very natural operation. So, any other questions? So here, this ring is generated by some familiar modular forms. C4, C6, the modular discriminant and its inverse. So C4 is the usual, yes. So it will be not a free module. So yeah, so because, well, quantum field theory is complicated, right? So you can imagine that you have some boundary condition, there's some degree of freedom, and then you stack some other degree of freedom. But then you can deform it to make it a way simpler theory. So then you can imagine that there can be actually some torsion for this module. It will not be always a free module. Yeah, so at first sight, it sounds like a free module, but it's really not. Right. And then this modulo familiar relation. So C4, that's C4 and C6, two of the asymptote series. And C4 is a theta function for the E8 lattice. So it's 1 plus 240 Q plus dot dot dot. And then, so there is a map from the ring of topological modular forms to that of the modular form. But this is neither surjective nor injective. So there is something in the kernel. These, fortunately, are all torsions. And then here, it's also not surjective. So it can only hit some modular form, not some other modular forms. So in particular, some modular forms cannot be partition function of 2D theories, 2D supersymmetric theories. So let me just very concretely describe this in some degrees. So at degree 0, it's actually an isomorphism. So this is actually just a polynomial in J. So what is this telling you? Is that, well, actually, any polynomial in J, that's a partition function of a supersymmetric 2D supersymmetric theory. So that's good. And what is pi 1 TMF? Here, what's the meaning of this 1? So what happened is that here, when we are talking about trivial theory, it's trivial up to a gravitational Chern-Simons term. So namely, the theory can have gravitational anomaly. And this degree exactly measures this gravitational anomaly. And that's compatible with how modular form appear as elliptic genus of supersymmetric theory. Because here, the modular weight is indeed half of the gravitational anomaly. So if here we have gravitational anomaly d, now this side you will have weight d over 2. Okay, but for pi 1, there's not anything in weight 1/2. So all of this has to be torsion. And this turned out to be the following. Basically, Z2 coefficient polynomial in J. And that's generated by a two torsion element that I will denote by eta. And I will not explain this too much, but this eta can also be viewed as elements of a stable homotopy group of spheres. So this is a Z2. And it's the same Z2 that physicists use to understand the Witten anomaly. Pi 2 of this is actually again the same, and that's generated by eta squared. And then pi 3 this is the 24, and it's generated by another element from the stable homotopy group of sphere. This is often denoted by nu, and it's in pi 3 of S. S, that's so pi star S, that's a stable homotopy group of spheres. So pi 1 of S, you can think of this just as a pi 4 of the 3 sphere, or pi 5 of the 4 sphere, so on and so forth. And similarly here, you can think of this as pi 8, or maybe slightly larger, pi 7, sorry, 9 of the 6 sphere. But it's also useful to think of this as an image of a particular element in pi 7 of S4, generated by the Hopf vibration. So there is a familiar Hopf vibration that also hit these elements. That's a Hopf vibration of the 3 sphere over the 2 sphere. And this is the one associated with the 7 sphere over the 4 sphere. Anyway, so so this ring of topological model form has very interesting structure, and given the amount of time, I cannot fully explain it. But the goal is to talk about certain modules, TMF modules associated with 3D theories. Yes. No, not yet. So here, this is about theories. 3D for 3D theory, it will be a module over of TMF. It will be a TMF module. So these are simple examples. So this is in pi 1, this is in pi 2, this is in pi 3. And these are topological modular forms that are not modular forms. So one can also think of this from a point of view of physical theory. So what's the physical theory corresponding to this? This is actually S1 sigma model, 2D 0, 1 S1 sigma model. It has index 0 because, well, the order characteristic of a circle is 0. So if you look at the vacuum of the theory, it will be a fermionic state and a bosonic state. But the statement is that this is actually a non-trivial theory. There's not a way of deforming this to actually the trivial, well, Susy breaking theory, although it's index 0. And this is generated by sigma model to T2. And this is generated by sigma model to S3, basically. Yeah, so let's give some very simple example of TMF modules. So one example is, in a sense, already given here. For the trivial theory, the TMF module will just be TMF itself. And one can actually make this slightly more interesting by considering a level D gravitational transamination theory. And then it will be, again, one copy of TMF, but now shifted in degree. So these are, in a sense, boring examples. And then one slightly more interesting example is U1 gauge theory. In this case, well, this is a supersymmetric theory. So if you again compute this Witten index, that will equal to 0. And again, you worry that maybe this theory can be deformed to a theory that breaks supersymmetry. But the TMF module associated to it is TMF plus TMF1. I don't know how to interpret it as a sum of delta function. So the Witten index for this theory, I think it's just 0, because again, if you look at the ground states, bosonic and fermionic state will be paired together. So maybe when you're talking about delta function, you are thinking again of family of theory, where there is some, I don't know. So, but here, you see that this is actually a refinement of 0. Because this is in some degree, this is shifted. So it's like bosonic and fermionic. And in a sense, they can cancel to give you 0. But as a TMF module, it's not the trivial module. So how to think of this? This is also can be viewed as what the TMF cohomodule associated with S1, or equivalently, homotopy class of map from S1 to this TMF spectrum. And this one way to understand this S1 is that this is actually the dual photon. Namely, you have a boundary condition. In the bulk, you have a dual photon. That's like a 3D sigma model to S1. So on the boundary, you would naturally have a S1 family of boundary conditions. And that's, in a sense, captured by this. Whether it's dualizable. So, so for a certain class of theory, for topological theory, one expects that it's actually dualizable by considering incoming versus outgoing boundary conditions. But if the theory is more complicated, namely when you have infinite dimensional Hilbert space, then probably you would expect that it will not be always dualizable. This is expectation because for concrete computation, we only know the answer for like massive theories with finite dimensional Hilbert space. So then there's always a dual. But but this construction would work also for the massless theory. Then you have infinite dimensional Hilbert space, and you would worry about exactly that kind of issue. So U1 at level 1. This is TMF again. So all of this looks like free modules. But then you look at U1 level 2. This is already not free. So this is a mapping cone of nu. Yes? Yeah. So here I'm a shift. So there should be a shift. Yeah. So U1 level 1 is indeed just purely gravitational. And then, therefore, you actually expect that you would agree with this. And here I'm also, again, ignoring the shift. But what happened here is that if you tensor this over rational numbers, it has two copies of TMF. And that's expected because, well, the Hilbert space for this is two-dimensional, so it should be two copies. But then it will be two copies that are non-trivially glued together. So therefore, it's not just TMF plus TMF shifted by 4. It's instead a mapping cone of these degree 3 elements. And for U1 level K, the story would be more complicated. So it will be certain rank K module, and there is a fit into some long exact sequence. And using this, one can kind of answer the question about phases in 3D. Because there, one expects that, well, on the other side, the TMF module should really be TMF CPK-1, which is in a sense the sum of these two terms, because this is a reduced version. But all these maps, they are non-trivial. And one can show that this is actually different from just this. So that should tell you that this U1 level K should actually be in a different phase with the CP K minus 1 sigma model. Was there a question? Or? Yeah, yeah. Yeah, they have the same index. So here, so if one ignore this and also this, they have the same index. Because, well, this is a K minus one dimensional, this is one dimensional. This is reduced version. Yeah, yeah. So any other question? So I have maybe tried to convince you that this kind of new invariants will be useful in the study of the dynamics and structural phases of 3D theories. So let me mention like how to generalize this to other dimensions. So in 1D, we have already encountered the Winter index. And the analog of this is again, well, by looking at boundary conditions. But boundary condition, that's going to be, in 1D system, will just be a state. So the space of boundary condition, that's just working with a Hilbert space. And indeed, we kind of believe that working with the Hilbert space is slightly better than working with the index. Because, for example, for this wall crossing, if one really understands what happened to the Hilbert space, well, then one gain a slightly more insight compared to just what we can learn from the Witten index. For 2D, then the boundary will be a 1D theory. So then it will be either a K theory or KO module. Because, well, similar to the statement that TMF classify 2D theories, K theory or KO theory classify 2D theory with or without certain time reversal symmetry. There, one can use this to actually distinguish between different 2D T-cavities. But, well, 2D T-cavities are somewhat too simple, so there are not much interesting application there. Well, but for 2D dynamical theories, this can be more interesting. 3D, as I mentioned, one can get TMF modules. Just cohomology. It's supposed to be with C coefficients. So I think there's a way of arguing that. So here, naively it's C coefficient because I'm just having. Yeah, yeah. So here, yeah, I was just saying that naively you get C because this is supposed to be boundary conditions. And then, well, in other cases, boundary conditions are classified by, well, TMF or TMF modules. But now you have a boundary condition of a 1D theory, and that's just a state. And the state is only naturally a C module, or maybe C star module. But maybe there's a way of actually think of it in terms of a Z module. And I haven't fully understood this story. Maybe with supersymmetry, somehow you can argue that this can be made naturally into a Z module. But just But there's a story of Soul Techner where they talk about this hierarchy, and there I think they just use this with the C coefficients. That's what naturally happens when they talk about this Euclidean field theory in a certain manner. So there you only have like partition functions. So then, um, on the boundary, it will be 1D n equals 1. So in the bulk, it can be anything that would allow you to have 1D equals 1 boundary condition. So how about higher dimensions? In higher dimension, actually, this kind of naive story terminates, and I don't know what would be a replacement for it. But you can do something else. You could again get TMF module by looking at space of 2D 0, 1 defects. And in fact, this work in any dimensions, so 4D, 5D, and higher. Instead of looking at boundary conditions, one look at the space of surface defects with 0, 1 supersymmetry. And again, it's going to be a TMF module because you can stack 2D theories on top of it. And actually, there can be another way of getting TMF modules by simply reduction or compactification. So I think we have all seen a lot of this kind of procedure. So you consider some theory, reduce it on some manifold with different choice of backgrounds. Because there are many ways of doing the reduction to get to 3D. And in principle, that give you a collection of TMF modules. And in some very nice cases, one can actually get some TQFT over the ring of topological modular forms. But maybe there's no time to say more about it. But I think that this invariants can have some interesting applications, and not only in 3D, but also in higher dimensions. And maybe there one can use this to distinguish certain phases, like those in gauge theory in 3 dimensions. That would be more interesting. So, thank you. You mean like this? Yeah, so for sigma model, what's a boundary condition for like a sigma model? So one have fields on the boundary and then coupled to the bulk field. The bulk field is just a sigma model. So then one have actually a CP K-1 family of 2D theories. So that's one naive way of talking about this boundary condition. And then that naturally is associated with either this cohomology or this is the same as a map from homotopy classical map from CP K-1 to this TMF space. And that's also what one really expects because that's really a family, a CP K-1 family of 2D theories. So, so this kind of module would be naturally associated with sigma models. For non-abelian consignment theory. The problem is that then on the transaminase side, it's not clear how to do the computation, except for level 0. For level 0, it will be one copy of TMF. But for a higher level, you expect you get some TMF module with certain rank. And on the other side, it will be TMF associated with either Grassmannian or some other target space. But then we don't have a good way of really computing this from the transaminase point of view. So I didn't have time to fully explain the computation in the abelian case. So this is using some work by Lurie. So he has a machinery that basically can be used to understand this for abelian transaminase theory. Not only rank 1, but rank n, or arbitrary rank. But then in a non-abelian case, well, we know that in some cases they can be abelianized, then maybe it still work. But in general, there's no good machinery to work it out. Yes. Yes, that's right. So there are maps from TMF module to KO module. And then in this example, exactly one see that after reduction, they become the same. Um, yeah, I don't know how to systematically, from the math side, come up with such examples because I think many details of this reduction is not completely understood. So it kind of understood at level of modular forms, or maybe slightly more refined version, KMF. But in general, it's not so clear. Then from physics, the question is also kind of tricky. We want to look for different 3D phases that become the same in 2D. And there are some candidates, right? We look at certain parameters that got complexified, and maybe that's one way of getting those. But then the harder challenge is to argue that these phases are actually different in 3D. So, right. It's supposed to be invariant under good deformations. And namely, this would include those deformations of gap theory that would not close the gap. So that's similar to like the case of Witten index. If you expect it to be an invariant and under some deformation, well, you would not want to close the gap. So here, this would be sensitive to the other kind of phase transition that I talked about for the weight index. If a pair leave the vacuum, then weight index would not know about it, but this would change. So there you would also have some discontinuity. So it's slightly finer.